Okay, back to your questions. Homework, if you want to hand them in. Even if it is late, just hand it in. I mean, don't wait for the next week. But I mean, if you bring it tomorrow, that's also fine. As long as it doesn't become your habit, all of them. Next Monday, we won't have lectures, so it's already holiday. Now back to your questions. The ceiling is also nice to look at. So one of you were mentioning these identical particles, distinguishable particles, indistinguishable particles. Any questions on them? Okay, so your favorite numbers. What's your favorite number? 3. Okay, another favorite number?
11.
Okay, chapter 3, problem 11. So the question is, we have the law, not PV to the PV is equal to constant, not PV to the gamma is equal to constant. We have PV to the n. This is constant. And then the volume is changed from V1 to V2. So in the PV diagram, this is the PV to the n is equal to constant diagram. So this is a V1, it is compressed to V2. Let's say this is P1. This is P2. No, but let me reverse them. This is P1, this is P2. So this is the process from A to B. What is the work done? What is the heat given to the system, if any? So how should we proceed?
So it should be an adiabatic process.
Well, you see, for an ideal gas, the adiabatic process is PV to the gamma is equal to constant, where gamma is Cp over Cv. And for a monatomic ideal gas, gamma is just 5/3. Monatomic ideal gas meaning that we ignore any internal structure of the atoms. But here n is arbitrary, we don't know. For an adiabatic process, what is delta Q?
0.
Delta Q is 0 anyway. So this is an arbitrary process. But it is such a process that during the process, PV to the n being some number, is constant. If in that process n is equal to 1, it's an isothermal process. If during that process, if this is a monatomic ideal gas and during that process n is 5/3, this is an adiabatic process, but it doesn't have to be. So how should we go?
We can calculate the area under the curve.
Okay. So how do we do that?
We can write P2 in terms of P1 by using PV to the n constant.
Okay. Now? Is this correct? Okay, now from this expression, how do I obtain the area under the curve?
We can find the slope. That's no slope.
Okay, the slope will be constantly changing.
Equation of the curve. We can find the equation of the curve.
How? Hmm? So what is the equation of this curve? Hmm?
And first the n can be calculated by defining the values at point A and B.
Well, you see, n can be anything depending on your process. And it's already given that you are changing the volume from V1 to V2. Those are things that you can control. And you can also control n by determining what kind of process you are talking about. So those are all determined. And those are all free to choose. And once you choose those, okay, P2 is fixed. You cannot play with P2 without changing n V2. What do you mean by equation of the curve? Let me ask that question. Yeah, that is my equation already. And I can, in terms of the known values, I know P1, I know V1. Do I know P1? Yeah, well, I can determine P1, let's say. This is P1, V1 to the n. So this is the equation of my curve. So if you want to obtain P as a function of the volume, P is P1, V1 to the n divided by V to the n. Okay, this is the equation of the curve. Now what?
Can just integrate PdV.
Integrate PdV to find what will I obtain if I integrate this? The work. Which is from V1 to V2, P1 V1 to the n divided by V to the n, dV. This is P1 V1 to the n, V to the 1 minus n, V from V1 to V2. And so this is equal to P1 V1 to the n divided by 1 minus n times V2 to the 1 minus n minus V1 to the power 1 minus n. This is delta W. If you like, I can simplify it even further, just multiplying it out. And remember, P1 V1 to the n is the same thing as P2 V2 to the power n. So delta W is P2 V2 minus P1 V1 divided by 1 minus n. Okay, this is the work done. What about the heat?
We can find the temperatures for P and V values from both.
How?
And we can find the
Okay,
change in internal energy.
what should I write?
PV equals KT,
KT
not KT, pardon.
and KT. So,
And for P1 and V1, we will have a
temperature.
temperature T1 or T2. And we can find the change in internal energy from the CV.
Well, delta U will be CV times delta T, so which will be CV divided by NK, P2 V2 minus P1 V1. Here, of course, we are assuming that CV is equal to constant, which will be valid for the ideal gas. Classical ideal gas, let me correct myself. And delta Q. And we have the first law, delta U is equal to delta Q minus delta W, which tells me that delta Q is equal to delta U plus delta W, both of which we already know. So do you have any questions? Your friends did not. So I'm asking them questions. So what is your favorite number? Hmm? Hmm? Our favorite natural number? 3. Okay, we are going from chapter 3. Your favorite number? 7. Okay. Okay. How do you prove this identity? So the question is this one. Cp minus Cv. How can we calculate that? Then eventually we will relate it to a logarithm of Q, which is the partition function, etc. But let's stick with this one. Now, what is Cp? Do you remember the definition of Cp?
Specific heat for constant pressure.
Which is?
dq dt.
Okay, dq by dt. Of course, this is at constant pressure. So you see, we said that dq, the heat given to the system, depends on how we give the heat. So here the process is at constant pressure. So we are giving heat to the system at constant pressure. The temperature of the system will be changing, and specific heat is just the air ratio, which is the same thing as TdS by dt at constant pressure, or let me write it in a more proper way. This is the specific heat at constant pressure. And at constant volume, well, it's basically the same thing, but this time it is not evaluated at constant pressure, but rather it is evaluated at constant volume. Now let's look at here. We have the Cp, which is a derivative with respect to temperature at constant pressure. Here we are taking a derivative in Cv. We are taking the derivative with respect to, again, temperature, but this time at constant volume. If you look at the right-hand side, all the derivatives are with respect to volume at constant temperature. So essentially what we will be doing is making a change of variables. In Cp, the variables we are considering are P and T. So we are taking the derivative with respect to T at constant pressure. And all the other terms in that equation are actually derivatives with respect to not pressure, but no, with respect to temperature, but at constant volume, not at constant pressure. So we should make a change of variable from PT to VT. Now the question is, how can we do this change of variable? Well, there are certain derivative identities that are also quoted in the book, but I personally find this Jacobian a useful tool to do this change of variable. Do you remember the Jacobian? What it is, the definition? Let's assume we have two functions, f and g, of variables x and y. The Jacobian is defined as this matrix. So kind of, this is the f, this is the g, this is the x, this is the y. Well, you can see the rows and columns exchange, but essentially this is the idea. Now, where do you see it? For example, in multidimensional integrals. Let's say if you are integrating over f and g, but you would like to convert it to an integral over x and y, then you multiply it with something. And that something is nothing but the determinant of this Jacobian. No, the absolute value. Well, the easiest way to remember which one is up, which one is down in that fraction, well, you can just hypothetically imagine as if you are canceling x and y's here. And you will be left with f and g in the numerator. So f and g in the numerator is equal to f and g in the numerator. Now, why is it useful? This is equal to 1 over well, it will be easy to prove this once you prove another identity. Let's assume f and g are functions of x and y, but then x and y are themselves functions of u and v. Then if you just multiply the Jacobians as a matrix product, it is just derivative of f and g, the Jacobian of f and g with respect to u and v. In a sense, this is like the generalization of the chain rule for one variable to two variables. And let's say f and x Jacobian with respect to y and x. This is nothing but derivative of f with respect to y at constant x. F and g, y and x. Let me try define the Jacobian itself as the determinant. This is equal to g and f, y and x, f and g, x and y. Well, if you just change the position of f and g, well, if you look at this matrix, changing f and g is just switching the rows. But if you switch the rows, the determinant changes sign. So here we have a minus sign. Here, if you exchange x and y, in that case, In this determinant, you are just exchanging the columns. Again, if you exchange the columns in a matrix, it's the determinant changes sign. So that's why we have that minus sign over there. Now let's come to our problem. We have Cp, which is the derivative of the entropy with respect to temperature at constant pressure. I can write this in terms of Jacobians as the Jacobian of S and P with respect to T and P. P in the numerator and in the denominator. Well, it's trivial to show that this equality, well, this is kind of trivial to show. It's just the determinant of, if you write the Jacobian, the derivative of f with respect to y at constant x, then the derivative of f with respect to x at constant y. Then here we have the derivative of x with respect to y, that is 0. Derivative of x with respect to x, that is 1. If you just take the determinant, you just have the derivative of f with respect to y. Now, using that identity, I can convert this derivative into Jacobians. Now, what I would like to use is, I don't like t and p as my variables. I would like to use t and v as my variables. So this is equal to Jacobian of s and p with respect to t and v, 1 over the Jacobian of t and p with respect to t and v. Now you can just imagine, hypothetically imagine that you are cancelling this one with this one, and it leaves you the original Jacobian. Well, both, let's say the numerator is easy to write down. T is common, both in the numerator and in the denominator. So it's just derivative of P with respect to V at constant temperature. That's the numerator. In the denominator, we have the determinant of derivative of entropy with respect to T at constant volume, derivative of entropy with respect to V at constant temperature, derivative of pressure with respect to T at constant volume, and derivative of pressure with respect to V at constant temperature. This is this Jacobian over there. Just take the determinant. It's the determinant of a 2 by 2 matrix at constant temperature. And that determinant is del S by del T at constant volume, del P by del V at constant temperature, minus del P by del T at constant volume, and del S by del V at constant temperature. It is, so Cp is equal to T times, well, in the first term, this factor and this numerator cancel. They are the same thing. So I have del S by del T at constant volume. But remember, T times ds is nothing but dq. So this is dq by dt. dq by dt is the heat capacity. And this is the heat capacity at constant volume. So this is nothing but Cv. Minus what we have, T times dp by dt at constant volume. Here I have ds by dv at constant temperature divided by dp by dv at constant temperature. Well, let's see. This is just Cp is equal to Cv. So we now have Cp minus Cv. Minus, well, let me just rewrite it down. Well, you see, if you look at this derivative, it is nice. It involves pressure, volume, and temperature. If I know the equation of state, I can evaluate that derivative. How do I know the equation of state? Well, I can directly measure the equation of state. I can determine the pressure, the temperature, and the volume. Those are easy to measure. Similarly here, it involves only P, V, and T. So that's also easy to measure experimentally also. Well, here we have a problem. Not a problem, but it would be nice to also express that derivative in terms of P, V, and T. Well, Maxwell's relations are great help over there. Do you remember Maxwell's relations? For example, we had du was TdS minus PdV, which told us that T is just derivative of U with respect to entropy at constant volume, and P was minus the derivative of U with respect to V at constant entropy. Since they are the first derivatives of some function, if I take their derivative of T with respect to V, of course here I'm taking S and V as my variables, so derivative of T with respect to V at constant entropy, this means that how the temperature changes as I expand the gas in an adiabatic process. This is, on one hand, the second derivative of U with respect to first S and then V, but I can exchange the order of second derivatives. But this derivative is nothing but minus P. So the derivative of temperature with respect to volume in an adiabatic process, how temperature changes in an adiabatic process, is actually how pressure changes if I change the entropy of the system at constant volume. Well, how can I do that? If I add heat to the system, the entropy will change. I will keep the volume constant, and I will see how pressure changes. So you see, here the Maxwell's equation, the nice thing about Maxwell's equation is it relates some observable in one process to other observables in other processes. So the left-hand side can be calculated in an adiabatic process. The right-hand side can be measured in a process at constant volume. And whatever the system is, this equation has to be satisfied. Now let's go back. I'm not really interested in this derivative. What I'm interested in how the entropy changes as a function of V at constant temperature. So first of all, my variables here are V and T. Now here, if I start from U, my variables are already S and V. How can I change my variables to T and V? So you see, when I look at du, in that equation, I'm expressing kind of U as a function of S and V. So that's why I have all the derivatives with respect to either S or V, including in my Maxwell relation. I'm taking derivative with respect to V at constant S, or I'm taking derivative with respect to S at constant V. But what I'm interested in is V and T. Now this is V over here, fine, but I have to exchange T and S. How can I do that?
Free energy.
Yeah, free energy. You see, du is equal to TdS is nothing but the differential of T times S minus S times dt. So du minus Ts is minus S dt minus P dV. So this is what we call the free energy, U minus Ts. But this will tell me, if you just follow all the same treatment, you see S is the derivative of the free energy with respect to temperature. If I take the derivative of S with respect to V at constant temperature, it will be the second derivative of F. Just change the order of the differentiation in that second derivative, and that would just give me the derivative of pressure as a function of T at constant volume. So this is nothing but del P by del T at constant volume. That second derivative, that derivative of entropy is actually equal to the factor multiplying it. So this is in fact our expression for Cp minus Cv. Now this is the square. Well, you see, this also already tells us something. The numerator, the temperature is a positive quantity. This other factor in the numerator is the square of something that's a positive quantity. So except in the numerator, we already know that all those factors are positive. If you consider the numerator, you are keeping the temperature fixed. If you change the volume, you expect the pressure to decrease. So that's a negative quantity. Derivative of pressure with respect to volume at constant temperature should be negative. Increase volume, that means delta V is positive, dV is positive. The pressure should drop. That means dP is negative. The ratio will be negative. So this quantity is always larger than 0. So Cp is always larger than Cv. Well, how to see that dP by dV at constant temperature is positive? Well, you can also look at this one. Let's see. We know that the entropy is 1 over T. Well, no, let's write this one. Entropy is a maximum. Whatever the variables are. So the second derivative of entropy with respect to its variables, this should always be less than 0. This will already imply that dP by dV at constant temperature should be less than 0. You can write the pressure as a function of, as a derivative of the entropy. So this dP by dV will be somewhat related to the second derivative of entropy. This was another way to show it. Anyway, so this is not all of the question. This is our thermodynamic relation between Cp and Cv. Whatever your system is, up to this point we made no assumption, no approximation whatsoever. We just used laws of thermodynamics. Cp minus Cv, whatever your system is always given by that expression. There is no exception to that. Now we can apply it, if you like, to the ideal gas. Now what do we need? We need dP by dt at constant volume. Well, for the ideal gas, pressure is nKT by V. So dP by dV at constant temperature will be minus nKT over V squared, or let's write that as minus P over V. That is the numerator, the denominator. In the numerator, we have del P by del T at constant volume. This is Nk over V, which is just P over V, P over T. So let's go back. This is our Cp minus Cv. Which is equal to minus T. Okay, derivative of P with respect to T is P squared over T squared. Divided by derivative of pressure with respect to volume is minus P over V. Well, this temperature, one of them cancels. This pressure, one of them is cancelled. Minus signs, they cancel. So it's just PV over T, which is just okay. So if Cv is equal to 3/2, then that tells us that Cp is 3/2 Nk. Cp is 5 over 2 Nk. And gamma, which is Cp over Cv, is just 5/3. This is something we had already done before. Now let's try to convert our final expression to the form given in the book in terms of the derivative of the logarithm of q with respect to v. What was q? How do we define the partition function? The formal definition.
Sum over exponential minus beta overall energy.
Overall microstates, not the energy. You see, this equation is like the F is equal to ma in mechanics. In mechanics, everything starts with F is equal to ma. All the problem solutions will start with F is equal to ma, unless you are using Lagrangian mechanics. And here, almost all our derivations will start with the partition function, this one. If you are doing Lagrangian mechanics, all your computations will start with L is equal to T minus U. And here, this is our equation. Whatever we do, we will be doing with this one. And this was equal to e to power minus beta a, where that a, okay, here I use the symbol F, it is that a, it's the free energy. So a logarithm of q is actually minus beta times a. And remember, the a is minus x dt minus p dv. Now let's see, here we have the derivative of the logarithm of q with respect to v at constant temperature. Well, derivative of the logarithm of q with respect to v at constant temperature, beta is just 1 over kt. So if t is constant, beta is constant. This is minus beta derivative of a with respect to v at constant temperature. But this is nothing but, you see, from here, if t is constant, dt is 0. If you divide dA by dv, you obtain minus p. So p is nothing but k times t times the derivative of the logarithm of q with respect to v at constant temperature. Now, in our original expression, Cp minus Cv is just written in terms of the derivatives of P. Well, I know what P is. This is minus T times minus Kt, let's say this, K squared T, sorry, derivative with respect to T. P is T times the derivative of the logarithm of Q with respect to V at constant T. That T derivative is at constant volume. All of this thing squared. This is the numerator. And the denominator, I have K. This is at constant temperature, so Kt is constant. Derivative of logarithm, the second derivative of the logarithm of Q with respect to V at constant temperature. So T's, they cancel. One of the K's cancel. So I have Cp minus Cv. Okay, I have what remains. Cp minus Cv is minus K. It's just this expression over here. Okay, so what you need to know, at least to do some manipulations in thermodynamics, you need to be able to change your variables. So that is what we did over here. Instead of using T and P as our variables, we just converted into T and V as our variables. So Jacobians is, it might seem complicated at first sight, but it does simplify. It's much more simpler than alternatives. The alternatives is just kind of randomly playing with the variables and chain rule. So it simplifies significantly. The second thing is this one. I mean, the rest of the semester will be mainly to calculating this partition function and taking its derivatives, and then interpreting the results.
To get rid of the differentiation under constant pressure, could we just use Cp equals to del enthalpy over del T under constant volume? Try to cross it further.
At constant, no, del T at constant volume. Good luck. You can try. I mean, there are almost infinitely many ways you can solve a given problem. Whichever one you find more easy. Then you would probably say that H is equal to E plus PV. So the H by dt at constant V, this will be equal to dE by dt at constant V plus V dP by dt at constant V, I suppose. No, sorry, this is not at constant V, at constant P.
But this is enthalpy, not the. So it has PV inside instead of
No, you cannot have PV inside.
PdV. I mean, E plus PV under constant pressure or volume, energy, internal energy change the same, but the PV part we are interested in.
You see, you have du plus PV is equal to TdS plus PdV, no, VdP. So T at constant pressure, du plus PV is equal to TdS. And what you are looking at is ds by dt. TdS by dt at constant pressure. So this is Cp. So Cp is dH by dt at constant pressure. Cv is du by dt at constant volume. So again, the variable is P.
Is del PV over T under constant pressure or constant volume bigger?
Del PV by del T at constant pressure is P times del V by del T at constant pressure. Del PV by del T at constant volume is volume times del P by del T at constant volume.
This will give you the change in PV from T1 to T2.
During which process?
This PV change should be independent of P or V.
You see, the thing is, okay, it will change the the change in PV from state A to state B as you increase the temperature. But how do you increase the temperature?
Isn't it stable?
Yeah, you see, you just imagine a process.
It's a function of T,
PV as a state function, yes, PV is a function of T. But keep in mind that here we are considering mainly, so what you are saying is PV for the ideal gas is already NKT. So the derivative should be NK, not necessarily for everything. You see, if you just consider two nearby processes. Now you are saying that let's just imagine two nearby points in phase space. I already know what their change is in PV. So the point in the PV space already gives me what PV is. I just divide it by how much the temperature changes. I already know the temperature change in that process. So del PV by del T should be independent of how I go from point A to point B. But you see, let's see. PV. So let's assume that you want to calculate del PV by del T at constant volume. Okay, so what do? You just take 2 points that have the same volume and look at the change in PV during that process. Okay, so let me just put delta PV1. This is equal to delta 1 PV divided by delta T. If I know the PV, if I know the equation of state, I already know T, delta T also. So delta 1, I know what delta 1 PV is, I know what delta T is. But let's also compare it with del PV by del T at constant pressure. Well, how do I calculate them? I take this point, I take nearby point at constant pressure, and I look at this one. This is my delta 2 PV. Divided by delta T. Let's say this is delta T, delta 1T, delta 2T. So when I'm looking at these differences in PV, I'm not taking two states, two same states. So those two derivatives are essentially completely different things. In one of them, I'm just looking at looking at the difference between two states that correspond to the same volume. On the other one, I'm looking at two states that correspond to the same pressure.
They are on the same isothermal line.
I don't know.
But they have the
Why
same,
should they be? You see,
they have the same temperature. Yeah, if you are integrating over the same temperature in the constant volume and constant pressure case, they should be an isothermal. They should be on an isothermal line.
I don't see why.
Because in the first process, you said we have a differential.
You
If
see-
integrate,
You see, also keep in mind that PV is equal to NKT. It's just a special case. It's not valid in general. It's only for the ideal gas. And for the ideal gas, I can tell you that these two derivatives are the same. But in general, I don't see why they should be the same.
if you have PV equals some function with temperature and some other things different from temperature, it should be the case. But if you have just temperature, PV equals to FT, then you should
Okay.
have
If that is the case, I agree with you. But in general, it's not the case. So in general, it shouldn't be. Now, I can ask the next question. How can I relate them?
Neyle neyi relate dediniz?
In general, can I relate this one with this one? In general. Just like we related CP and CV for a general system, not only for the ideal gas. Can you relate those two somehow? I won't give that as a homework. Because you see, most of the time what we try to do is, given an expression, try to write it in terms of something that can be evaluated using the equation of state. Both of these can be written in terms of the equation of state already. So I don't really know what the outcome will be, if there will be a simple outcome or not.
Step how the partition function becomes exponential minus
So this is the question. We have e to power minus beta ER, sum over all microstates. Then I claim that this was actually equal to e to power minus beta A, where dA is equal to SDT minus SDT minus PdV. How do we know this? Let me ask this one first. Right, you see, also this A over here is E minus Ts. So let me ask this question first. What is the entropy in terms of these exponentials in statistics? Okay, what's the entropy? K logarithm of omega. Well, this was one definition. Well, then we said that we can generalize this a bit. You see, this is K ln omega. Omega is the number of microstates. So I can write that as K times minus K times logarithm of 1 over omega times 1 over omega times omega, which we can also write as minus K times sum over the microstates of 1 over omega times the logarithm of 1 over omega. Why can I say that? Because in the microcanonical ensemble, we are assuming that, there are omega states, so this quantity over there is independent of my microstate. So this sum just brings me a factor omega. It cancels that 1 over omega, and I recover the original initial definition of the entropy. But you see, in the microcanonical ensemble, we are assuming that all the microstates have equal probability. And I have omega of them. If they all have this equal probability, each one has a probability 1 over omega. So this I can write as minus K times sum over all microstates, probability of the microstate multiplied by the logarithm of the probability of that microstate. Well, the nice thing about that final expression is that I can use it in any ensemble, not necessarily the microcanonical ensemble. Okay, so this is the general expression of the entropy that we use, whatever the ensemble is. Okay, so now let's go to the canonical ensemble. What is the probability in canonical ensemble? Probability of a given microstate. E to the power minus beta ER divided by Q. Well, the partition function is just a normalization in this probability distribution. So let's look at what is the entropy then. This is minus K, sum over all microstates of PR, which is e to the power minus beta ER. Well, let me just write PR. I will keep it as PR. Now, logarithm of PR is just minus beta ER minus logarithm of Q. And keep in mind, the Q is independent of which microstate I am considering. It's already a sum over the microstates. This is equal to K times beta times ER. K times beta times sum ER times PR plus K times logarithm of Q times PR. This is nothing but the average energy of the system. Well, sometimes we use U, sometimes we use E, whichever one you prefer. That's the energy of the system. And this is sum over all the probability should be just 1. So logarithm of Q is actually 1 over K times S minus K times beta times E. So beta times logarithm of U, logarithm of Q is, let's see, this is just 1 over T, 1 over KT times T times S minus E, then minus 1 over minus beta times E minus TS, but this is what we call A. Logarithm of Q is minus beta times A, or Q is equal to e to the power minus beta times A. And that's what we have over here. This is Q. Now it follows straightforward from the definition of the entropy. But then there is the other question. Okay, there we took a giant step. You see, we said that this expression is valid in the microcanonical ensemble. How do we know that it is valid in general?
Every ensemble itself is a microcanonical ensemble intrinsically. We consider the whole.
Yeah. I don't know how many people will be convinced by that. I don't know how many people will be convinced by that. You see, now what you can do is, let's say in the canonical ensemble, PR is equal to e to the power minus beta ER by Q. Let's look at its derivatives. Del S by del V at constant temperature. You see, if that definition of entropy is correct, this derivative should give me P over T. You see, one thing to check is, does that, no, del S by del V at constant, is what we know is du is equal to TdS minus PdV or dA. So ds by dV at constant entropy should be equal to P over T. No. ds over dV at constant energy should be P over T, and derivative of the entropy with respect to energy at constant volume should be equal to P over T. If you can show these, let's call this S prime. If S prime satisfies these relationships, then I can say that S and S prime, they differ by a constant. They cannot differ by anything. If their derivatives are the same, if you have two functions whose derivatives are the same always, then those two functions can at most differ by a derivative. And that they can at most differ by a constant. And then how to fix that constant? Well, in thermodynamics, that constant is fixed by the third law. So entropy should be 0 at T equal to 0. But in statistical physics, at T is equal to 0, the system is in the ground state, which is unique. So the PR is 1 all the time, 1 in one state and 0 all the remaining times. But 0 times logarithm of 0 is 0. And 1 times logarithm of 1 is also 0. So all the terms in that sum is 0. So that fixes that S prime is actually S.
Is the ground state always unique?
In quantum mechanics, yes. You see, let's look at this hypothetical problem. Let's assume you have a system with two infinite potential wells. So we have these two potential wells. Both of them are infinite. In this case, the ground state is not unique. So you can have one particle in the ground state on the left well, another particle in the ground state on the right well. So you have a degeneracy of the ground state in this problem. But this is not a realistic problem. You see here in this special case, the ground state is degenerate. Now let's try to, in a realistic system, what you will have is, well, these wells do not go to infinity. You have at most a barrier. Now, if there is a barrier, let's assume that we just restrict ourselves to this the Hilbert space of these two ground states. The Hamiltonian will be a 2 by 2 matrix. Let's say the ground state energy is 0. I can always shift my energy so that the ground state is 0. But since that barrier in a realistic system will not be infinite, there is a possibility of tunneling. But if there is a probability of tunneling, you see this Hamiltonian has energy eigenvalues plus or minus delta. These are the energy eigenvalues. So if you started with a degenerate system, the ground states were degenerate. But once you allow tunneling, that degeneracy is lifted now. You have a superposition of states. One of them has a lower energy than each one, and the other one has a higher energy. So because of this, in quantum mechanics, for a realistic system, the ground state will be unique.
Potential looks like Higgs potential. Is it the same?
Well, in the case of Higgs potential, the problem here is, you see, here we have a single degree of freedom, a single particle tunneling from left to right or right to left. In the case of field theory, I mean, that's why I'm insisting on quantum mechanics. In the case of field theory, a field is essentially an infinite degrees of freedom. So the ground state has infinite degrees of freedom. For one ground state to tunnel to the ground state, you have to have the tunneling of these infinitely many degrees of freedom, which is the probability is 0. So in field theory, this doesn't happen. Even, for example, if you have, let's say, a magnetic system, and we will study magnetic systems. If you go to the thermodynamic limit, you have infinitely many, you have a continuously degenerate vacua, and your system has infinitely many degrees of freedom. So this argument also there doesn't really work. So there are certain cases in which the third law of thermodynamics doesn't really work. Okay, let's give a break. And if you like, we can continue with the question that you prefer. Otherwise, I will keep asking your preferred number.